Hello and welcome to a late night edition of Geometry. Today we will cover section 2.3 on conditional statements and complete the guided notes. First of all, let's talk about what we will learn this episode. Start by skimming lesson 2.3. Predict 2 things you will learn based on the headings and the key concept box. Looking through the section, we can see the heading 1 is on if-then statements, and the concept is about conditional statements, and I can see their components include hypothesis and conclusion. So for the first thing we'll learn, we'll say we will learn how to form conditional statements with a hypothesis and a conclusion. Continuing on, after a couple examples, including using truth tables again, we find there are related conditionals. Related conditionals include converse, inverse, and contrapositive. And some of these are logically equivalent. So the second thing we will learn is how to create conditionals that have logical equivalence. Now let's start filling in our vocabulary as we read through the section. So cozy up and grab a cup of hot cocoa, and let's begin. If-then statements. A conditional statement is a statement that can be written in if-then form. The direction given below is an example of a conditional statement. If you would like to speak to a representative, then you will press 0 now. I think that's a reference to the telemarketer or IT help desk example above. An if-then statement is of the form if P, then Q. Recall that P and Q are standing in for full statements. In symbols, we have P arrow Q, read if P then Q, or if P implies Q, or you can see it as P leads into Q. So to define conditional statement, is a statement that can be written in if-then form. An if-then statement means if statement P, comma, then statement Q. The components of a conditional statement are the hypothesis. The hypothesis of a conditional statement is the phrase immediately following the word if. That would be just statement P. The conclusion of a conditional statement is the phrase immediately following the word then, statement Q. Notice the model here. Statement P is entirely inside of statement Q. Imagine you were standing inside these circles. If you are standing inside circle P, you know you are also automatically standing inside circle Q. So knowing P implies that you know Q is true as well. For our definitions, I would like to describe the hypothesis and conclusion a little more clearly. The hypothesis is the condition to fulfill, the statement immediately following the word if. And at the end of the conditional, we have the conclusion. It's the result upon that fulfillment, the statement immediately following the word then. Let's continue reading. When a conditional statement is written as an if-then statement, you can quickly identify its hypothesis and conclusion, because they are followed by those key phrases if and then. We'll cover the examples in a later video. Many conditional statements are written without using words if and then. To write these statements in if-then form, identify their hypothesis and conclusion. For instance, this sentence, points will be deducted from any paper turned in after Wednesday's deadline. Notice that this is a condition to be fulfilled. Papers can be turned in before or after Wednesday's deadline. If they are indeed after Wednesday's deadline, then the conclusion will be activated and points will be deducted. So we could rewrite this as, if a paper is turned in after Wednesday's deadline, then points will be deducted. Remember, the conclusion depends upon the hypothesis. It is a cause and effect relationship. Please note that the word if and the word then are not actually part of the hypothesis and conclusion. The hypothesis and the conclusion of a conditional statement can have a truth value of true or false, as can the conditional statement itself. Consider the following conditional. If Tom finishes his homework, then he will clean his room. Let's construct a truth table. The hypothesis statement, Tom finishes his homework, could be either true or false. The conclusion, Tom cleans his room, could also be either true or false. This gives us 4 different combinations. So the total conditional, if Tom finishes his homework, then he will clean his room. When both hypothesis and conclusion are true, the condition is true. If Tom does indeed finish his homework and he does indeed clean his room, then the condition is true. If the hypothesis is true, but the conclusion is false, the conditional is false. If Tom does not clean his room after he does in fact finish his homework, then he has not fulfilled his promise, and the conditional is false. Let's highlight this. This is a key phrase to remember. How conditionals can be false. Unfulfilled promises. Notice when the hypothesis is false, but the conclusion is true, well, Tom didn't finish his homework, but he could still clean his room. The conditional only indicates what will happen if Tom does finish his homework. He could clean his room, or he could not clean his room, even if he does not finish his homework. We don't know what will happen, and either one he does will not break a promise. When the hypothesis of a conditional is not met, the truth of a conditional cannot be determined. When the truth of a conditional statement cannot be determined, it is considered true by default. So let's go back and fill in our table. These are by default left as true. We're going to assume the best circumstances. If you didn't break your promise, then we will assume the conditional is still true. Because if it's not proven false, logic dictates it must be true. The result from the previous page can be used to create a truth table for any conditional statement. Here is P, here is Q, and P implies Q is always true except in the circumstance where P is true but Q is false. To show that a conditional is true, you must show that for each case when the hypothesis is true, the conditional is also true. To show that a conditional is false, you need only to find one counterexample. We'll practice that in the next video. Now on to part 2, related conditionals. There are other statements that are based on a given conditional statement. These are known as related conditionals. A conditional statement is a statement that can be written in the form if P, then Q. Notice the symbols P first, arrow leads into Q. For example, if the measure of angle A is 35 degrees, then angle A is an acute angle. This, you will note, is a true statement. The converse is formed by exchanging the hypothesis and conclusion of the conditional. That is to say, they will trade places. So we start with Q, and that leads to statement P. For example, if angle A is an acute angle, then measure of angle A is 35 degrees. This is not always true. Measure of angle A, if we only know that it's acute, could be 40, 45, even 50 degrees. So this conditional would be false. It's not guaranteed. The inverse is formed by negating both the hypothesis and conclusion of the conditional. Remember, to negate something means to give its opposite truth value using the word not. So not P implies not Q. For example, if the measure of angle A is not 35 degrees, then angle A is not an acute angle. While this is certainly possible, measure of angle A could still be 30 degrees or 40 degrees, and then it would still be acute. So this is also not guaranteed and is thus false. The contrapositive is formed by negating both the hypothesis and the conclusion of the converse of the conditional. So here we are negating, and remember the converse started by exchanging. The contrapositive does both. It states, if not Q, then not P. For example, if angle A is not an acute angle, then the measure of angle A is not 35 degrees. Acute angles are always less than 90, so if it's not acute, it must be more than 90, so there's no way it could be 35 degrees. This statement is true. Let's fill in some of our vocabulary now. The converse is formed by exchanging the hypothesis and conclusion of the conditional. The inverse is formed by negating both the hypothesis and conclusion of the conditional. And the contrapositive is formed by both negating and exchanging the hypothesis and conclusion of the conditional. And these are the related conditionals. Other statements based on a conditional statement, including the converse, inverse, and contrapositive. Let's continue reading. A conditional and its contrapositive are either both true or both false. Similarly, the converse and inverse of a conditional are either both false or both true. Statements with the same truth value are said to be logically equivalent. A conditional and its contrapositive are logically equivalent, and the converse and inverse of a conditional are logically equivalent. Note that we saw this in the provided examples. The original and the contrapositive were true, while the converse and inverse were false. If a conditional is true, the converse may or may not be true. By default, if we can't guarantee that it's true, we're going to say that that statement is false. You can use logical equivalence to check the true value of statements. Notice that in example 4, both the conditional and contrapositive are true. Also, both the converse and inverse are false. Well, now I feel like they just spoiled it for us. Anyways, let's finish our vocabulary. Logically equivalent statements are statements with the same truth value. At the end of example 4 is the check your understanding, so we are finished reading. Let's continue to the second page of notes. The main ideas are if-then statements and related conditionals. We're going to practice identifying the hypothesis and conclusion of each conditional statement. We'll circle the hypothesis and underline the conclusion. However, for the first statement, the entirety of the statement is not actually given. We only know if the sum of its digits is divisible by 9. Sounds like they're referring to some number. If you recall your divisibility rules, you will know that when the digits of a number, or the sum of the digits, is divisible by 9, the whole number is divisible by 9. I shortened that slightly so it would fit on the line. A number divides by 9 if the sum of its digits is divisible by 9. The sum of the digits is the hypothesis because that follows the word if. And when that happens, we reach the conclusion a number divides by 9. In the second example, if the measure of an angle is less than 90 degrees, it is an acute angle. Here's our keyword if. So the hypothesis must be the measure of an angle is less than 90 degrees. That's the condition to be met. When that happens, you know it is an acute angle, even though they didn't actually write the word then. Notice this matches our definition of acute angle. In fact, such a conditional statement can be used to create accurate definitions. And now, let's fill in the organizer for related conditionals. From conditional statements, we have 4 possibilities. The original conditional, shown as P implies Q. Its logical equivalence is the contrapositive. Symbolically, not Q implies not P. Notice that I have negated both of them and exchanged their positions. The other 2 conditionals are the inverse, symbolically negated, not P implies not Q, and the converse, which is exchanged from the original, symbolically Q implies P. And finally, to help you remember, when working with a conditional statement and its 3 related conditionals, what is an easy way to remember which statements are logically equivalent? Here's what I've come up with. Converse and inverse both end in verse, so they are in the same universe. The original and contrapositive like to stay positive. Note that that does not mean they will always be true, but they will match and try to stay in sync with each other. This concludes the guided notes for section 2-3. Come back for part 2 to complete the example problems from the section. So long, farewell, and enjoy the rest of your day.